What's the nature of voltage and current in a first order RL-DC network? Are they independent of time like that in DC resistor network? Do you ever think about it? Okay guys, it's me Abhisha. You are watching me on our channel Crack Easy, the place to learn how to crack easy exams. In this session, I'm going to share all about first order RL-DC network. You will learn all aspects of the response right from the start to the end. Let's get started. In fact, in a DC resistor network, the voltage and current are independent of time. But they are dependent of time in a network consisting of capacitors and inductors. Why it is so? That's what we are going to look at next. First of all, let's have a quick review on what is inductor, what is the nature of voltage and current in inductor, how they are related, etc. Basically, inductor is an energy storage element. As you know, resistors convert electrical energy into heat, but inductors and capacitors store energy which can be retrieved at a later time. They do not generate energy. Only the energy that has been put into these elements can be extracted. Thus, like resistors, inductors and capacitors are also passive elements. Alright, let me take you ahead. In fact, inductor works based on electromagnetic induction. When we twist a wire of finite length, it becomes a simplest inductor. If a current is made to pass through this, an electromagnetic field is formed. And if there is any change in the flow or direction of that current, the electromagnetic field also changes. This change of field induces a voltage VL across the coil, which can be mathematically expressed as VL is equal to L into dIL by dt, where VL is the voltage across the inductor, IL is the current flowing through the inductor, and this constant of proportionality L is known as inductance. Alright, you can see the symbol of an inductor here. Let us now find out the mathematical expression of current through an inductor. As I said to you earlier, the voltage across an inductor VL can be expressed as L into dIL by dt. From this equation, we can write dIL equal to 1 by L VL dt. Now, we are going to integrate both sides of this equation from 0 to t. So, we get integral 0 to t dIL is equal to 1 by L integral 0 to t VL dt. Integrating and applying upper limits and lower limits, we get an equation like IL of t minus IL of 0 is equal to 1 by L integral 0 to t VL dt. From this, we can write the expression of current IL of t is equal to IL of 0 plus 1 by L integral 0 to t VL dt, where IL of 0 is the initial current through the coil or through the inductor. Clear? Let me now take you to some interesting facts about an inductor. The first one, an inductor acts like a short circuit to DC. Does anyone knows the reason for this? As I said to you earlier, the voltage across an inductor VL can be mathematically expressed as L into dIL by dt. So, when the current is constant, correspondingly the voltage becomes 0, or we can say that an inductor acts like a short circuit to DC. Moving on to the second fact. Inductor opposes abrupt change in current through it. Based on the relation between voltage and current of an inductor, we can say that a small change in current within 0 time through an inductor gives an infinite voltage across the inductor, which is physically impossible. Finally, an ideal inductor does not dissipate energy. The energy stored in inductor can be retrieved at a later time. The inductor takes power from the circuit when storing energy and delivers power to the circuit when returning previously stored energy. But practically, an inductor has a significant resistive component since it is made of a conductive material such as copper, which has some resistance. That's all I want to say about an inductor. Let me now take you to next topic, which is nothing but first order circuits. Does anyone knows what is a first order circuit or why it is called so? In fact, first order circuits are those which contain only one storage element, that is one inductor or one capacitor. The total response of this circuit can be decomposed into natural response and forced response. So we can write the total response is equal to natural response plus forced response. The natural response is due to the initial condition of storage element. On the other hand, forced response is resulted from external input. Transient response and zero input response are the other names for natural response. Forced response is also known as steady state response and zero state response. Clear? I think it may be a little confusing for you. Don't worry, you will get a clear picture when we analyze first order RLDC network. But before moving on to that, it's better to have a quick review on first order differential equation. In fact, first order circuits are described by first order differential equation. So for analyzing these circuits, we should know how to solve first order differential equation, and that's what we are going to look at next. Here you can see a first order differential equation with the constant coefficients di of t by dt plus p into I of t is equal to q. The solution of this equation is I of t is equal to e raised to minus pt integral q e raised to pt dt plus c e raised to minus pt, where c is the constant of integration. Thus we discussed all concepts which are necessary to analyze a first order RLDC network. So it's the time to start our analysis. RL circuits. First we are going to find out the forced response, that is the response due to an external input. Here you can see in first order series RL circuit. Initially this switch is kept open, so no current flows through the circuit. At t equal to 0, switch S is closed and a current flows through the circuit. We are going to find out the expression of this current. So let us start the analysis of network by writing KVL equation of this loop for t greater than 0. Starting at this point in clockwise direction, first we observe this voltage source with the polarity mark in the order minus plus. So we add a term minus V to our KVL equation. Then the voltage drop across this resistor, which is nothing but R into I of t. Correspondingly, we add a term R into I of t to our KVL equation. Finally, the voltage drop across this inductor L, which is equal to L into di of t by dt. Correspondingly, we add the term L into di of t by dt. By KVL, the algebraic sum of voltages across the loop is 0. So we get minus V plus R into I of t plus L into di of t by dt is equal to 0. By rearranging this, we can write it as L into di of t by dt plus R into I of t is equal to V, or di of t by dt plus R by L into I of t is equal to V by L. Thus, we obtain the differential equation describing our RL circuit. Now, we have to solve this equation to obtain the expression of I of t. That's what we are going to do next. As I said to you earlier, this is the basic form of a first order differential equation with the constant coefficients di of t by dt plus p into I of t is equal to q. Comparing these two equations, we get the value of P as R by L and Q as V by L. As I said to you earlier, the solution of a first order differential equation with constant coefficients can be expressed as I of t is equal to e raised to minus pt integral q e raised to pt dt plus c e raised to minus pt. By substituting the values of p and q, we get I of t as v by r plus c e raised to minus r by l into t, where c is the constant of integration. For finding out the value of this c, we are going to apply initial condition. As I said to you earlier, the switch S is closed at t equal to 0. At t equal to 0 minus, that is just before closing the switch S, the current in the inductor is 0. Since the inductor doesn't allow sudden changes in currents, at t equal to 0 plus, just after the switch is closed, the current remains 0. So we can write at t equal to 0, I of t is 0. By applying this in the expression of I of t, we get 0 is equal to c into e raised to minus r by l into 0 plus v by r, or c is equal to minus v by r. Now we can write the expression of I of t as I of t is equal to v by r into 1 minus e raised to minus r by l into t. Thus, we obtained the forced response of a first order RL DC network. Next, we are going to plot this response in a graph. Here, the current I of t is plotted along y-axis and time along x-axis. It is clear that it is an exponentially increasing curve. Now, have a look at natural response of first order RL circuit. Here you can see a series RL circuit. The switch is placed at position A for a long time, and at t equal to 0 it is changed to position B. Now let us find out the expression of current through it for t less than 0. For t less than 0, the switch is at position A and we get a equivalent circuit like this. As I told you earlier, switch is initially placed in position A for a long time so that the circuit already reached its steady state. And this inductor acts like a short circuit since it is excited with a DC source. So we can write the expression for this current I for t less than 0 as I is equal to V by R. Hope it is clear. Next we are going to consider the condition t greater than 0, where the switch is placed in position B and we get a equivalent circuit like this. I of t is marked as current through this inductor. Now let us find out the expression of this current I of t. So we are going to write KVL in clockwise direction starting at this point. First we observe the voltage drop across this resistor R, which can be expressed as R into I of t. Then the voltage drop across this inductor, which is nothing but L into di of t by dt. As I told you earlier, this is the basic form of a first order differential equation with constant coefficients, that is di of t by dt plus p into I of t is equal to q. By rearranging this equation, we get di of t by dt plus r by l into I of t is equal to 0. Then when we compare these two equations, we get the value of P as R by L and Q as 0. Finally, substituting these two values in the solution of this equation, we get I of t is equal to C into e raised to minus R by L into t, where C is the constant of integration. Thus, we obtain the expression of current through inductor. Next, we are going to plot it. You can see it here. I of t is plotted in y-axis and time along x-axis. It's an exponentially decreasing curve. The current in the circuit is initially I0, that is V by R. In fact, the inductor stored energy in the form of electromagnetic field when it was excited with an external source for t less than 0. At t equal to 0, the external excitation or external source is removed, but still the current remains I0, that is V by R. Then the stored energy in the inductor is dissipated gradually through the resistor, and finally, when the total energy is dissipated, the current through the circuit becomes zero. You can see it here. It is approaching zero. Hope it is clear. That's all for today. If you have any doubts, please do let me know in the comment section. Thanks for watching. Thank you.